We're going to start this module by talking about some general chemistry concepts through the lens of organic chemistry. Now, don't get intimidated by what looks like the volume of material here. Most of it should be review. We're just looking at it a slightly different way. Now, we're going to start with bonding. In our chemicals, we have both sigma and pi bonds. So if I draw out this molecule here, and this molecule, this is acetone. Acetone has both sigma and pi bonds. So I have all of these purple bonds, and I'm going to change the color of one bond, and I'm going to change this, not that color. I'm going to change this bond to pink. So this is my pi bond. Everything else shown is a sigma bond. Now, sigma bonds are formed by end-to-end overlap, and that end-to-end overlap can be formed by s orbitals, p orbitals, or by hybridized orbitals. Now, hybridized orbitals is something we're going to touch on here in just a second. Hold that in the back of your mind. Pi orbitals, on the other hand, result from p orbitals that are next door to one another. Now, remember that a p orbital is shaped like a dumbbell. So when you have two p orbitals that are next door to one another, you can have this interaction. And that's what creates the pi of our pi bond. So we have pi bonds and we have sigma bonds. Now, most of the sigma bonds that we're going to interact with are going to be made from hybridized orbitals. Now, the general rule of thumb for hybridization is that the number of atoms and unbonded pairs of electrons on an atom are going to be equal to the number of orbitals that are involved in the hybridization. Well, that's a whole lot of words. What does that mean? Well, we have three different hybridization situations that we will be concerned with here. There are more and different hybridization levels, but these are the ones that we're going to be concerned with. We have sp3, sp2, and sp hybridization. See the exponents on these orbitization indicators here. The s has an exponent of 1. In this case, the p has an exponent of 1. So if we add those together, that means we have 4 orbitals here. This means we have 3 orbitals. This means we have 2 orbitals. Now, when a carbon atom goes to bond, carbon comes in. Remember the valence electron thing and the electron configurations and the orbital diagrams where we compare those valence electrons, and carbon looks like this. Carbon comes in with 4 valence electrons. But what happens is these orbitals will hybridize, and they hybridize so that one s combines with 3 p's in order to get those electrons as far away from one another as possible. That gives 4 places for bonds to be created, for carbon to share its valence with other atoms. Now here, if we take this situation here, then what has happened is each one of those hydrogens comes in with its electron and fills those orbitals. That's how we are sharing these bonds. This is just a quick and dirty review of what covalent bonding means. Now, because all of those orbitals have hybridized together, we have created four orbitals of the same energy. So we are sp3 hybridized. Now, as soon as we create this pi bond, when we create this pi bond, what happens is one of these p orbitals is occupied. So I only have 1, 2, 3 orbitals that hybridize, and then I have this p orbital by itself. It still has 1 electron from carbon, but now it has an electron from oxygen as well. So that p orbital is occupied. It's taken up by this pi bond. So when that occurs, what we have here, this is sp2. You see the 2 p orbitals and the 1 s orbital have combined and hybridized. So when you have 1 pi bond, you have an sp2 hybridized orbital. When you have 2 pi bonds, so if we had something with a triple bond, let me just quickly draw that out. If we had a triple bond, 1, 2, 3, let's see, nitrogen likes to make a triple bond there, then we would have to alter this a little bit more. Instead of having 2 p orbitals hybridized with the s, we would have 2 p orbitals that are now occupied, and they are occupied in pi bonds because each of these is a pi bond. The one on the bottom would be my sigma bond. So the sigma bond in all of the cases that I've shown you here are created from hybridized orbitals. So you do need to be familiar with this, the sp3, sp2, and sp hybridization, indicating how many pi bonds we have and where electrons can be found. Now, there will be cases where you have lone pairs of electrons that may be in a p orbital. And we'll talk about those specific cases when we get there, but we're not going to be talking about them today. We need to talk about some generalizations and make sure everyone is on the same page. So in a nutshell, that is the hybridization that we will be interested in. Now, I'm also supposed to cover formal charge. And we don't use formal charge all that much, so I'm not going to dwell on it. But just as a brief recap, so your formal charge is going to be the number of valence electrons. You subtract the number of bonds made with that atom, and then you subtract the number of non-bonded electrons. So for carbon, that's easy. If I'm going to look at, say, this carbon here, carbon comes in with 4 valence electrons. There are 4 bonds showing, and there are no unbonded electrons with that carbon, so the formal charge on that carbon is 0. So if I look at the oxygen, oxygen comes in with 6 valence electrons. There are 2 bonds showing, and what we don't show when we show this kind of a structure is we don't always show the lone pairs of electrons. You do need to know that there are 2 lone pairs of electrons. Now that is 4 non-bonded electrons. So the formal charge on that oxygen is 0 as well. Now what we use formal charge for mostly is to determine what is going to be the most contributing Lewis structure for a resonance form. Now, resonance is a way that we can increase stability, or stability is increased with resonance forms. So resonance is the movement of a lone pair of electrons and a pi bond. And when this happens, what you're doing is you are delocalizing that electron density. So if I turn this from acetone into acetic acid, then what happens is, or let's do acetate. That would be even better. So what happens is one of these lone pairs of electrons will migrate down to form a double bond here, which pushes this double bond, because carbon's octet will not be violated, up to here. So we have these 2 resonance forms. And the resonance forms look like this. Now it also looks like we have some configurational isomerism occurring here. But those electrons are delocalizing. We're spreading out that electron density so that there is less electron repulsion. That increases the stability of the ion.